Okay, so we'll go to the next part. If there are questions, just let me know. The attendance register. Here's the attendance register. Can you pass it over? It was on the floor, I noticed. Like, is that a, trying to say something? Okay. Let's see if I put this on the floor and see if Bob forgets about it. Which is a good try. It's a good try. So we're going to talk about a few things. We're not going to finish it all today. Graphs, n-dimensional data, icons, and interaction techniques. Actually, it's quite a lot. It's going to take 2 or 3 lectures. We're going to start out with graphs. Now, Dan Archibald likes graphs quite a lot. So I guess he covered graphs in some detail last semester. Do you remember how many weeks he talked about graphs for?
I think we spent 1 week at the beginning and then we went back for 1 or 2 weeks. Yeah, I think a total of 2 or 3 weeks.
Okay. We're going to just cover it in like 20 minutes.
We did a lot of graph functional calculations.
So Dan is the expert on graphs. I'm not the expert on graphs. But maybe my novice introduction will be a little bit more accessible because I've tried to compress it down, all the graphs, into like just 5 slides. You could easily take a module only in graphs and graph theory, easily. You could just have one module dedicated to that topic. Graphs have their own like conferences. You can go to a graph drawing conference. They have their own books. You can get books about graph drawing. So it's a sole topic. We're just going to give a short introduction because you can use graphs in assignment 1. And you'll see graphing tools. You'll notice that they're there. Anybody notice a graphing tool yet? Nodes and links and all that stuff? Anybody use Doxygen?
Yeah.
There's a graph. Graphviz, yeah. Who knows what a graph is? Can anybody define a graph? Anyone want to take a stab at it? It is not that easy of a question. Did the attendance register? Did I get it back?
You can put it on the floor.
Okay. So a graph is just a set of nodes and edges that connect them. That's all. That's all a graph is. At least for the purposes of this lecture. So when we have a graph, when we're laying out a graph and presenting it, we want to optimize some properties of the graph. So here's a sample graph, by the way. And you can imagine trying to optimize some of the properties of these graphs. So when you're designing a graph, you have basically 3 objectives, basically. There are others, but the 3 big ones are here. To optimize the length of the edges between the nodes. So if the edges are too long, it's hard to derive the connections between 2 nodes. If I have a node over there, and a node over there, then it's hard to see the connection, unless there's just one connection. Right? The longer that edge is, the more difficult it is to derive the connections or to see the connections. Too short is also bad, right? If the edge is too short, you can't see it at all. And there's something in the middle that's like the best length. So you want to optimize the edge length, minimize edge crossings. Right? If you have lots of edges crossing, it's also very difficult to read and interpret. If there are too many edge crossings, you can no longer follow the connections between edges because they will overlap. And then, when you do have edge crossings, you want to maximize the edge crossing angles. So what's the maximum angle you could have between two edges? $90, yeah. So you want to try to get the edge crossings to be 90 degrees if you have edge crossings. If two edges are crossing, but they're crossing in like an angle of 1 degree, there's a 1 degree subtended angle, it's difficult to distinguish the two edges from each other, right? It's hard to see them, to tell them apart, right? So whenever you're looking at a graph, the algorithm in the background that's positioning the nodes is trying to optimize these three factors. Trying to optimize the length of the edges, minimize the crossings, and then maximize the edge crossing angles. And here's an example. This one, if we look at this one, we can deduce that in this example, really the algorithm is focusing on the first two, optimize length of edges and minimize edge crossings. It's looking at those two things, and it's not worried about the third one too much. Right? We can just deduce that by looking at the graph. And the challenges are, what happens when your graph has 1 million nodes? What do you do about that? If you have a graph with 1 million or 1 billion nodes? What happens if you want to represent time in your graph? How do you represent hierarchies in your graph? What about labels? If you want to put labels against all the nodes or even against all the edges, where do you put the labels? And then how do you represent multivariates or more than one variant in a graph? These are the big open graph challenges. Small univariate graphs that are static are not, you could say, are kind of a solved problem. Here's a famous graph. Anybody know what that is? Yeah? I recognize some of these names. I'm surprised. Oliver Clark. Where's Oliver Clark? What is this? Train map of what? Okay, you can't see it?
Yeah, that's just
Is it because it's not bright enough here? Because it's not very bright. It's just your eyes?
Yeah.
Okay. It's the most famous graph in the world, arguably. I think it is. It's good to know. Can anybody help out? Oliver? Connor Clarkson? Let's see. Connor, what do you think? Yes, London. Very challenging. Now, this is what I do in my free time. I look at the graphs and I say, oh, what are the properties that have been optimized? Right? That's what you do. And this is a famous example. So this was not like this was somebody putting the nodes and the edges down manually, not just like writing some software that does it automatically. But even in this case, it doesn't matter. You can still see, okay, what was this person trying to optimize? Well, they were trying to optimize the length, the edge length between the nodes. Right? They decided that, for example, the nodes should be separated by that edge length, generally speaking. It's not too long to make so the connection is easy to read. They were also trying to optimize the edge crossing angle to maximize the edge crossing angle, right? So all the edge crossings are at 90 degrees or 45 degrees. They're usually big. And then that's the thing that's hard to optimize with London, is that other one, the length between nodes. Well, that's one of the so like if you're trying to get from like here to here, it's very difficult. With the, you have to really study the London map. At least I do, if I want to get all the way across. But you can see that these three properties, whoever did the London Underground map worked very hard to optimize those three properties. And you can see where it breaks down a little bit. Like the London Underground becomes, it's difficult to see and understand what's happening in these areas, isn't it? Like, it's difficult. Like you think there's a stop there, and maybe you can get to from one station to another, but you're not exactly sure unless you've done it already. Anybody have that feeling in London sometimes?
It's not too scary. Like if you take the four corners and you overlay them up, the actual town. Too scary.
No, it's not. We're going to come back to this topic, actually. Or maybe we don't. Maybe we come to it today. Okay, yes, we come to it today. So, psychic powers in the room. Look, there it is. That's the same, that's like virtually the same thing. Here's London from the tube view. Now if we go to Google Maps and take the satellite view of the same area, that's what it looks like. Now if you were in London, has anybody here been to London? If you were lost in London, has anybody been lost in London before? If you're lost in London and you went up to somebody and said, "I'm lost, can you show me where I am?" And they said, "Yeah, you have two options. I can show you on this map if you want, or I can show you on this map where you are. Which one would you choose?"
Depends on where you are. If you're on the edges, that's not very useful. You're between those two nodes in the corner. You're anywhere in between that.
Okay, we could do an experiment. I'm going to give you this map.
Depends on where you are. Just saying.
I'm going to tell you where you are on this map, and then I'll give it to you. I'll put a little circle and say, "Okay, now you know where you are." So they're the same data, kind of. It's like it's two different views of the same thing. They're radically different though somehow, aren't they? Like it would be difficult to just take, say, "Okay, you're here. Like you're here. Now get yourself unlost. Like find your way." Usually, when people go to London, they bring this map with them. Usually. Anybody know why they're so different? Like, how do you describe that difference? You can see that they're very different somehow. There's something very different, but on the other hand, it is the same city, and in some ways, some of the information is the same. It's a difficult question, so I won't interrogate it. Exactly, well done. So this is also called a topological map. That's what a graph is. It's a topological description of something. And what is a topology? It's the same definition of a graph as a graph. It's a set of nodes and edges, the edges that connect the nodes. That's a topology. So this is actually a topological description of London, you're just given the nodes, general positions, and then the connections between the nodes. So because you're trying to get from like one place to the other, and that's all the information you're given. The rest is stripped away. This one is, this one does have that information in there. Like the London Underground is there. It's hard to see, but like I didn't like remove it from the satellite photo. You might not be able to see it because it's underground, right? Some of the elements. This, you can call this a geometric view. So one's topological and one's geometric. So why am I using the term geometric? It's because the geometry is preserved here. The exact locations of everything are preserved. So we're getting everything at the exact locations. So it's more data, it's too much data in this case. We don't want all of the data. Otherwise, we would print out maps like this on our way to London, right? And bring this with us. We don't want everything. We don't want all the information. And why am I explaining that? It's because I'm hoping that you'll now understand this word topology, because I'm going to use the word topology a lot throughout the module. So you can have a topological view of anything, and you can have a geometric view of anything. Graphs happen to be a topological view of data. Here's another example of a graph. Right, this is also from the tool for Hinoda's Many Eyes. Right, it's an automatic graph node layout program, and it also automatically places the labels. And the way it resolves the overlapping edges is it says, okay, you can click on any node, and then the edges to all the other connections will be highlighted. And the other edges are turned into a grayscale. Right, so there's an interaction that resolves the overlapping edges. Use interaction to resolve that. This one is another graph layout algorithm that hopefully you've seen before, a lot of you have seen before. It's featured in Doxygen. In Doxygen, you can generate graphs in your software automatically. Now, like when I look at that diagram, that automatically generated Doxygen diagram, I'm like shocked. The first time I saw that, I was shocked. Are you serious? Somebody has done this? Somebody has written an algorithm that can automatically generate collaboration graphs in your software? Like, that is amazing. I thought it was absolutely amazing. I still think it's amazing. But it's really, really sophisticated, very, very advanced graph drawing. Did anybody ever test out Doxygen on a really big program, like with 100 or 1,000 classes? Anybody ever look at that or see that? It still works. It still works. It can draw graphs with 1,000 nodes, 5,000 nodes. It's amazing. It's absolutely amazing. And it will do that. It will analyze your software automatically and then output the graphs. It's a really great tool. I used to work for a company called AVL before I moved here. It's like a commercial, real-world company. I was a software developer. And this software was not pretty. And one of the problems or the challenges, let's say, is the software wasn't documented at all, which isn't too surprising. Happens a lot in the real world. And one day I said, it would be really great if the software was documented. It would be really great because when one software developer leaves the company, then they bring all their knowledge with them, and none of it is retained at the company. And they said, oh, okay, that sounds interesting. Like one of my managers said, that sounds interesting. And then I showed the lead developer, I said, there are tools for documenting software. I said, really? He said, yeah, one of them's called Doxygen. And he looks at it, oh wow, that looks really interesting. Anyways, I introduced it to the lead developer, the manager, whatever. And they said, okay, we're going to use this from now on. And then they ran the graph drawing algorithm on their commercial software that they had already been working on for 5 or 6 years. And it worked. Like, it didn't crash. It was able to draw a graph of the whole piece of software. I was absolutely shocked. And immediately you could see that the software was totally bonkers. It wasn't very well organized. But it was, I'll never forget that day. It generated an image that was like, it went from like the ceiling to the floor. You had to scroll up and down to see the whole image. You couldn't print it out on the A4. It was huge. I was just shocked. I tried to save it, but I lost it in the meantime. Here's another example of a graph drawing algorithm in real life. This is not like software, but that's hardware. Anybody recognize that? Anybody have ever like opened their electronics and looked at the motherboard, for example? This is where you see it on a motherboard. It's a graph. It's a graph, and it follows those principles. Anybody notice the principles being followed here? So one of the golden rules, no edge crossings. Like this one has to be optimized for no edge crossings. No, that's a hard rule. And even when an edge does take a turn, it's always very obvious. It's like the angles in the edges are optimized. They're always 90 degrees or 45 degrees. And the other optimization is to try to, the length of the edges, right? The edges have to be, the length has to be optimized. They can't be too long and they can't be too short. So it's like a real world graph drawing in hardware problem. Anybody? Okay, I wrote the answer on the slide. It was me outside. Here's a flow, topological view of flow, the vector field, right? These are critical points, sinks and sources, and then they have connections. This is a recirculation zone. It's connected to something called a saddle point, and it's connected to another recirculation zone. And then that's the graph embedded inside the geometry. And then here's another abstract graph. And look, this one has not been optimized very well. Right, lots of edge crossings. The angle at which they cross is not optimized. It's not 45 degrees or 90 degrees generally. Right, the lengths are kind of all the same. Graph edges don't have to be straight, so they can be curved. And that has useful properties. You can call straight edges first order edges. You can also have curved edges, and they're also called higher order edges, inspired by higher order approximation. Now, why is this advantage? Can anybody see why this could be advantageous just by looking at it? Rodri, that sounds like a question for you, actually. I can imagine you. It could avoid edge crossings. It could minimize optimize edge crossings. Maybe it's not that obvious from this drawing. Can anybody imagine another reason, Carlo?
If you have weight edges, you will have values. Apart from the left of the thickness, you will have Asian the same value.
That's true, and that's the next slide. We're not even on that slide yet. If I look at this one, it's got like Carl said, it has directed edges. Like this edge has a direction, and this edge has a direction, and this one does too. Imagine I'm starting at A, and I want to know, and then I'm also looking at D. If I'm at D, I don't know where, and I go back 2 edges. There's an ambiguity, right? If I arrive at D, I could have come from B, right? B, C, D, but I could have also come from E, E, C, D, E, C, B, C, D. So everybody see that? So like I could start at E and then arrive at D. I could start at B and arrive at D. So if I'm at D and I want that information about did this path start at B or E, I cannot tell from this first order straight edge graph. But if I curve the edges, I can resolve that ambiguity. Right? Because starting at D, only B really can get to D. And in this version, we cannot get to D from B. We have to come from E or C. So by adding a curve to the edge, you can go backwards by more than one node and find out where you came from more than one node prior to that. That's the idea. That's the idea. And yeah, this has actually been applied to real data, right? So in this example, if we're looking at some marine biology, for example, imagine a penguin in the state of floating. Well, prior to the state of floating, the penguin could be in a dive state or a fly state. Maybe that's not such a good example because I don't think penguins can fly. It's something like a cormorant or something that can fly, a bird that can fly. So it can go from the float state to the dive state to the float state, but it can also go from the fly state to the dive state to the float state. And if we use straight edges to depict that same information, we wouldn't be able to make a distinction between like this source, this origin, or this origin. I hope that makes some sense. We can also add information to the edges. Right? We can make the edges thick. We can add texture to the edges to convey more information. For example, how often is a transition from one node to another node made? If that transition is very frequent, we can make the edge thick. If it's very infrequent, we can make it very thin. And I will just give a little. There's a demo of this application, and we can look at it. Right? It's called the BioExplorer system. Just for anybody that is curious to see, what that looks like in a real application. I thought I had the URL here. Maybe I didn't. show you where that example is of an actual graph being used for an actual purpose. Somewhere here. I guess I should start using the search functionality. Oh, there it is. So we won't go through the whole example, but this is an actual visualization system that's studying the motion of marine animals from marine biology, deep sea animals, and birds, cormorants, and penguins, and those types of animals. And each node represents a behavior of the animal, like one behavior. So we saw some examples like diving, flying, floating, swimming, eating. And each edge in this graph represents the transition from one behavior to another. So what does the animal do before it decides to eat? Right? Or how often does it go from swimming to floating, and floating to diving, and those sorts of things? And that's what these nodes represent, different animal behaviors. And then the thickness of the edges represents how often that transition happens. And then he's added textures to the edges, and the textures are animated, so you can see which direction the transitions happen. Anybody ever here watch the Jetsons? This reminds me of the Jetsons for some reason. All the people flying through the streets. Anyways, that example is on YouTube with a voiceover that's explaining every piece of the system. So you can have a look at it if you're interested. Okay, any questions? I can see that everybody's can't wait to continue on with the assignment. Want to get to the lab, dying to get to the lab. We will stop here then if there are no questions.